Greetings everybody. Let's continue our discussion of eigenvalues and eigenvectors by taking a short detour and passing through the Gram-Schmidt orthogonalization. So suppose that we're given a collection of vectors v1 up to vn, then we say that that collection of vectors is going to be orthonormal if and only if we do the dot product of v sub I and v sub j, then we get 1 if the I is equal to j and 0 otherwise. So really what we're saying with that is when we take the dot product of a couple of vectors in there, that the vectors dotted with themselves have length 1, so they're unit vectors, and they're pairwise perpendicular to one another. So if we do the dot product of vi and vj with I not equal to j, we get 0. That's showing that the angle between them is going to be pi over 2, and so that one gives us so that they're just going to be mutually pairwise perpendicular to one another. So the theorem that we can get with this is that if v1 up to vn is a basis for a space S, then there exists an orthonormal basis, w1 up to wn, for that space S. Now the idea is the procedure we're going to use is just kind of a chopping down a tree procedure, in that we'll just slowly, one whack at a time, we'll just take a piece out until we eventually get to the result that we want. And so because we've got v1 up to vn as a basis in and of itself, remember what that means is that they are linearly independent and that they span the space. Well, since they're linearly independent, v sub 1 can't be 0. We can't have any 0 vectors in there. So v sub 1 can't be 0, and so the dot product with itself, which remember what this is, it's just the square of the norm, is not going to be 0. And so if we divide by the square root of v1 dotted with itself, then we just essentially take v1 and normalize it so that this thing has length 1 to it. If we go through and we check that out, and we look at w1 dotted with w1, well, that's our 1 over the square root of times v1 and 1 over the square root of times v1. Since these are scalars, we can pull them to the outside, and in pulling them to the outside, that gives us a square. So we have v1 dotted with v1. The square kills off the square root. We get v1 dotted with v1 in the numerator, v1 dotted with v1 in the denominator. They cancel out, and so we get length 1. And so w sub 1, sure enough, is going to be a unit vector. Kind of the next step with that is we remember our vector projections from Calc 3. And so if we've got one vector w1 and we've got another vector v2, then we can say, well, how much of v2 is going to be in the direction of w1? Now the formula for getting that is just going to be the dot product of v2 with w1 in the numerator divided by the dot product of w1 with itself in the denominator, and that's our scaling factor times w1. Well, in the special case when w1 is going to be a unit vector, our denominator is 1, so that cancels out, and so we just hit v2 dotted with w1 times w1. Now, if we look at the difference of v2 minus that projection, then we claim that that thing's going to be orthogonal to w1. Well, if we do the dot product of that vector with w1, so that's w1 dotted with this, well, we can distribute across, so what is that v2, that projection? It's going to be v2 dotted with w1 times w1. Well, we can distribute our dot product across the difference, so we have w1 dotted with v2 minus w1 dotted with v2 dotted with w1 times w1. Well, this v2 dotted with w1 is a scalar. We can pull that to the outside since our dot product is linear. And so what happens then is we have w1 dotted with v2 minus our scalar times w1 dotted with itself. Well, w1 dotted with itself is 1 since it was a unit vector. And since our dot product is going to be symmetric, these two are going to be equal, so they cancel each other out, and we get 0. so that this result that we have, V2 minus the projection, is going to be orthogonal to W1. Well, if we take U2 being V2 minus that projection, then we normalize that, then we get a unit vector that's in the same direction as U2, which is perpendicular to W1. And so W2 is going to be perpendicular to W1. And since V1 and V2 are linearly independent, then W1 being parallel to V1, then U2 is not going to be equal to 0. So kind of how do we know that that's going to be true? Well, if we kind of replace all of our values in here with going back to V1 and V2, then this gives us a non-trivial linear combination. It's got to be non-trivial because that coefficient is 1. So a non-trivial linear combination giving the 0 vector, but since V1 and V2 are independent, that can't happen. And so we have that an orthonormal set now. So W1 and W2, they're both unit vectors. W2 is perpendicular to W1. It was constructed that way. We took out the projection. And so our span of V1 and V2 is equal to our span of W1 and W2. So we can take two vectors. So if our set has two vectors in it, we've shown that we can construct a orthonormal set from that gives us the same span. Now, how do we do this in general? Stay tuned and we'll see that one coming up in the next video.